All right, so this is some chapter 12 information regarding bonding in solids and the structure of solids, and pretty much it's an extension of what we've already talked about in terms of intermolecular forces and what is causing particles to stick together when they form liquids or when they become solids. The strength of those attractive forces then are what the melting point is dependent on, the boiling point, etc. So what we're looking at when we talk about solids is just how the particles, when they're stuck together, are arranged and what those particles in that arrangement look like. So meaning, are they ions, are they atoms, are they molecules? And so that's what we're going to take a look at, is the different types of bonding in solids. And really you'll see a lot of overlap between this topic and the bonding types. And so here we go. All right, so there's 4 general bonding types of solids, and we see them here: metallic, ionic, covalent network, and molecular. So right off the bat, we recall metallic, ionic, and covalent were the bond types that we've studied. Metallic solids, again, the characteristic of a metallic solid and metallic bonding is that there's a network of highly delocalized electrons. We describe that as that sea of electrons that, again, are attracted to all the cations, all the metal cations in the structure, and are free to pass throughout that structure. We have ionic solids that consist of cations and anions that are attracted to one another, and it's a repeating pattern of positive and negative particles over and over again throughout the structure. Next, we've got covalent network solids, and covalent network solids are, well, they're just like they sound like. They contain covalent bonds. What it is, it's an atom at, so you notice this picture on the lower left-hand side here. There are atoms at each of the lattice points, so that's the particle that repeats throughout the structure, but they are held together by a series of covalent bonds. So that's why we call it a network, because you might also see these referred to as like macromolecules or macromolecular solids, and that's because it's kind of this unending network rather than a definite, discrete, small molecule containing only just a couple of atoms. So in comparison, when we look at what is a molecular solid, well, that also contains atoms that are covalently bonded together, but like we see depicted here, we have an oxygen and 2 hydrogens, so these are water molecules. But each water molecule, that's what repeats throughout the structure. That's the entity that repeats at each of the lattice points, and what's holding those together in place is just intermolecular forces and not covalent bonds themselves. So we'll notice that the molecular solids are going to have much lower melting points than the covalent network solids, because they're held together only by, or those particles are held in place only by their intermolecular forces and not the much stronger covalent bonds that covalent network are held together by. Okay, so again, we should recognize that we describe most solids as being crystalline solids, and what that means is that the atoms are arranged in a regular pattern. The other type of solid that we can have is amorphous, and so this is not what we typically picture or describe when we have talked about solids, but the particles are still touching. They have less, they're not able to slide past each other like in a liquid, but they don't have that characteristic arrangement of atoms like we have always pictured with crystalline solids. We've also already talked about alloys, but just as a reminder, again, alloys are a combination of 2 or more elements. Typically, it's mostly referring to mixtures of metals. There might be some non-metal components mixed in. So here's a list of common alloys. And again, the addition of, or the production of a mixture, so the reason we're adding one type of atom to another and making a mixture is that they can accentuate and change the properties of the metal that's in the majority. So for example, if I wanted to have a certain better conductivity or a different hardness or strength, by adding a certain composition, certain percentage of another element, you can achieve a different set of properties. You can kind of manipulate the properties of what the original substance normally has. We should be familiar with the two types of alloys. So here they are again, substitutional, which just means that the second element that's added in takes the place of the original atom in the structure. So, if I have a mixture as shown here, where they've got gold and silver on the left-hand side, the majority of the structure is gold, but they have some silver atoms that are in place of some of the gold atoms in that repeating crystalline structure. So that's what a substitutional alloy is that you literally have an atom of another element that is substituted into that structure for the atom that's in the majority. And then the second type is a interstitial alloy, which, as you can see from the picture here, so we've got the smaller atoms are placed in between, and that's what the inter prefix should remind us of. So the small atoms are placed in between the spaces in the lattice of the metal atoms. So those are the two types of alloys. Again, they should still have some characteristic properties of metals like we've discussed before, but the formation of alloys alters the properties a little bit, depending on what you mix together. Then we've got metallic bonding, and typically, actually metallic bonding only happens between metal atoms, and unlike nonmetals and metalloids that if they're going to bond to other nonmetals or metalloids, they do so covalently. But when we look at what metals do, if I just look at all the metal atoms kind of lined up, the bonding is stronger than what we would observe if I just had atoms of another type that were lined up. So that's what this is saying here, that it's stronger than a dispersion force, metallic bonding. But they're not exactly forming covalent bonds like the other nonmetals and semimetals are. So what we're looking at is, again, there's a collective effect of a large group of metal atoms together that produces the properties that we observe in metals. Okay, so again, we describe metallic bonding as, like a group of cations. Our valence electrons are loosely held. So then the cation of this metal atom is attracted to the electrons of the neighboring metallic cation, and vice versa. And again, the electrons are kind of free to move throughout this structure. And so we refer to the electrons as being delocalized, meaning they don't stay local to one particular atom or between two particular atoms, like when we describe covalent bonds, or rather they're delocalized, so they are spread out over the structure. Again, this delocalization of electrons is really the reason for the special properties of metallic solids, which is their conductivity, ductility, malleability, and so forth, which we've already talked about earlier in here. All right, the molecular orbital approach is actually something that helps to kind of fill in the blanks as to how and why metals can conduct electricity and what's going on with their electrons. Again, you can read about this in the book and look at the depiction, but we're not going to find this as a question on our test in any way, shape, or form. But again, molecular orbital theory is a different way, a different approach at explaining and looking at why are metals able to do what they do, where their electrons. And so the idea with molecular orbital theory is that the bonding orbitals for a structure of a whole bunch of metal atoms basically becomes this, again, it's a band of or a region where you're likely to find those electrons. And, as we have a large number of metal atoms in the structure, there becomes this kind of continuous band. So the orbitals are kind of, over this range of energies throughout the structure. So again, you can read a little bit about that in the book. But again, molecular orbital theory is a little bit beyond the scope of what we need to do in here. All right, next we've got ionic solids. So again, we've got the alternating pattern of positives and negatives. We know that because there's attraction from all sides from the ions on the ions, that's why we have varying melting points. That is also why we have the brittleness. Right? So if the structure gets shifted a little bit, then we're going to have these like charges repel apart, and that's why the solid breaks apart if if we are able to shift those ions. And there's a lot of information in chapter 12 regarding the types of lattices, and we don't really need to worry about that for right now. But obviously, depending on the size of the ions, what the ratio of the ions are, how they come together, and how the crystals are shaped will vary. And so that's something that we might look at in a course later on down the line. But what we need to know about ionic solids is their properties, and that it's a structure made up of an endless array of the positive and negative pattern. All right, and lastly, actually I don't think this is lastly, this is molecular solids. They are made up of molecules, so molecular solids are made up of molecules, and it's those molecules that, once they are slowed down enough, they will stick together, and again, they align themselves in a ordered pattern. So we're talking about a crystalline solid made up of a repeating pattern of molecules. And how that's different from covalent network is, again, covalent network still has covalent bonds, but again, it's not one defined molecule that repeats over and over again. So like if I look at this depiction of diamond, here's an atom, here's an atom, so the atoms are all bonded together by covalent bonds, and there's 4 covalent bonds off of each of the carbon atoms, and so there's no one, like if I were to put my finger on one of these, or put my cursor on one of these, there's no one cutoff point where I could say, okay, here's the end of one diamond molecule, and then here's the start of another one. So it's this, unending network of covalently bonded atoms that, as a result, have very high melting points, tend to be very hard substances. We know diamond's the hardest substance on Earth, and depending on how the atoms are bonded together, that will change the properties a little bit. So, for example, graphite has again, only contains carbon atoms, but because it's kind of these 6-sided rings and they lay in sheets, instead of having covalent bonds holding together the sheets, those sheets are held together by attractive forces. Well, that makes the difference in those properties. But again, it is still this unending pattern of just atoms covalently bonded, which makes it different than having the discrete molecules like in the molecular solids. Oh, there's graphite, just to show you what I was talking about. So again, still an unending network of the atoms bonded, but just not, they're not covalently bonded this way as well. So that gives graphite its slightly different properties than diamond. Okay, so there's a section about polymers. You can read through that, but again, that's kind of beyond the scope of this course in terms of studying them extensively. But I think it's a good idea to just have some familiarity, because we might see, we can still look at questions regarding bonding molecule shapes around the different atoms in the chain. And again, this is really getting them into organic chemistry, where we see these long chains forming. So that's why it's a little bit beyond the scope of our course. One thing that I think is useful to mention is just the differentiation of these terms. So a monomer is the unit that repeats throughout the structure. And the polymer then is, we have many of these units connected together. But the monomer is like the repeating unit throughout the structure. So I think it's kind of useful to know what that means. It is exactly what it sounds like once you know what a mer is. And that's it for solids from chapter 12. So those are the things you need to know. Again, there's a little bit more about nanoparticles, polymers. You should read through that, answer the questions. But really, we should be familiar with the difference between a crystalline solid and amorphous solid, and then the 4 crystalline solid structures, which again are differentiated by their bonding types or what's at the lattice point. So we have ionic, molecular, covalent network, and metallic. I think those are the ones. Did I mention metallic? So molecular, ionic, metallic, and covalent network. So again, those really are made up of the bonding types that we talked about in Unit 3. And again, what defines each of those solids, or what differentiates them, is what is the repeating unit throughout the solid and what's holding them together, what types of forces. So that's it for chapter 12, and there you go.